Hello, everyone, and welcome to the Boston Plastic Recycling webinar series. I'm Carolina Mejia, Senior Innovation Project Manager from Mondragon Corporation and leader of the dissemination, communication, and exploitation activities of the European project Primus. Today, I'm going to host the second chapter of our webinar series related with the legacy flame retardants in recycled plastics. For this job, we invited another European project denominated Creator. With their help, expertise, knowledge, and experience, we will provide background information on flame retardants, the current situation and new trends of flame retardants, the regulation and standards associated, as well as checking best practices for manufacturing and recyclers. So the structure of the webinar can be found on the right part of the screen. So you can see that the first part will have an introduction where we are going to explain the objectives of the webinar and why we are collaborating with Creator. Then the legacy flame retardants, trends and current situation. Then we will check the regulations and standards associated, and then we will check the best practices for manufacturers and recyclers. So for this job, as I already told you, we invited the Creator Project and some of our Primus partners that you can see in our cameras. We have Kevin Moser from Fraunhofer ICT, Lane Tack from ICL, Tom Carries from Coolrec, and Mathilde Tabot from Plastic Recyclers Europe. So thank you all for being here, and well, we will start the webinar. As you can see in the last part, we will have a round table to further understand the impact in the near future with these substances in issue. And at the end, we will have the attendees questions. So if you have any question related with any of the presentations, please write down your question in the chat. This is quite important. And we will be collecting all the questions for the end of the webinar. And then in the attendees questions, we will ask our presenters your questions. So we will start for the first part. So the objective of the Boston Plastic Recycling series is to unravel the latest updates and good practices of plastic recycling. So as I already told you, this is the second chapter. And the Primus project will, with close collaboration with other R&D projects, will present innovations that will and are shaping the future of the circular economy for plastics. So the objective of this webinar is to take a deeper look at the background information on flame retardants, their use in plastic, and their historical, actual, and future trends. We will also discuss current regulations and standards, as well as testing and analysis techniques for identifying legacy flame retardants in recycled plastics. So we will explore as well the best practices for reducing exposure to legacy flame retardants, including actions that manufacturers and recyclers can take. So today's webinar, I already told you, we will have Creator as our R&D project that is collaborating with our Primus project, Primus, and well, for this webinar, as we are collaborating with Creator, we have different similarities in our objectives. Both projects want to turn waste streams into a full circular model. So we first want to implement ways to collect secondary raw material, identify the presence of flame retardants, remove these contaminants from the materials, and finally reuse these materials in different pilots. We also want to develop a recycling value chain for post-industrial and post-consumer. We want to improve the plastic sorting process as well as mechanical and chemical recycling. We also are decontaminating we are also working on decontaminated pretreatment analysis to eliminate the substances, especially the flame retardants, and produce new technically and safe compliant recycled materials to use the high added value products and components. So for the first part, Kevin, Moser, and myself will present quickly the objectives of both projects. So Kevin Moser is Creator's Purification Process Work Package Leader, and he works as a group manager in the Polymer Engineering Department of Fraunhofer ICT. He holds a PhD in Applied Material Science and is specialized in tailoring polymer materials and processes. His main areas of competences are the crystallization of polymers, advanced polymers processes, and the functionalization of polymers and polymer recyclates. And I will briefly present myself, that I will present the Primus project. The Primus Communication, Dissemination, and Exploitation Manager, and I hold an architect degree with 3 masters in urbanism, innovation, and project management. I have experience in circular economy, Industry 4.0, and smart cities R&D projects, and I'm working as a senior innovation project manager at Mondragon Corporation. So the first part, Kevin will present the Creator project. Please, Kevin, take the control and the floor, please.
Yes, thank you. Thank you very much, Carolina. And thank you for your kind introduction, as well as for your invitation to present the Creator project within this webinar today. The Creator project is a collaborative project with 16 European partners, which started in June 2019 and ended yesterday, so in May 2023. The overall target of the Creator project was to remove toxic or non-legacy flame retardants from plastics to support recycling and subsequently to reuse of currently for recycling and not considered plastics materials. To achieve this, the implementation of all elements of the value chain, starting with the collection, identification, and sorting of polymers, were considered. Other key elements of the project were the development of a continuous extraction process using supercritical CO2 to remove the non-compliant bromine-containing flame retardants, the modification of the purified materials, and finally, for sure, feasibility studies in diverse end-use applications to demonstrate the potential to be reused in demanding applications. The extractive extrusion process is a new cost-efficient process for the purification of ABS, PS, and PC in double-digit kilogram scale. So at least we could achieve 20 kilograms per hour with the extrusion process. The process, as said, is a twin screw extruder-based process with specific modifications for the processing with supercritical CO2. Further, the Creator project delivered various solutions to all relevant steps in the value chain and demonstrated potential market integration for the purified materials in the sectors construction and demolition, electronic equipment, aeronautics, automotive, edge recyclers, and polymer part producers. Another very important element of the project was the development of an integral logistics concept and economic evaluation of the developed processes. On this slide, you can see the Creators Consortium. On the upper left side, you can see the partners, the key partners for recycling. For example, Erema, Coolrec, Tree, Geiger, Santexpel, Autoschuten, Volbas, and KLU. On the right side are the partners listed with the tasks for demonstration, so the end users. For example, Maya, Cycle Fiber, DRW, CIDO, and TCKT. LCA and dissemination was carried out by OVAM and ITRB within the project. If you wish more information, you can find them on the website, the Creator project website, or you can join our LinkedIn channel or directly contact our project coordinator, Yamami Konsari. Thank you very much for your audience.
Thank you, Kevin, for presenting and being here today. Okay, so now I'll present the Primus project in a really fast way. Well, the Primus project is a European project as well as creator, and that will improve the plastic recycling industry with new polymer recycling technologies for automotive and home appliances applications. So we have 4 demo cases, 2 of them in the automotive sector and 2 of them in home appliances. So the first 2 pilots in automotive, we are checking new polymers, recycled polymers for automotive interior and a cooling circuit system. And in the second sector, that is the home appliance, we have 2 pilots. We will check the recycled polymers for food contact demonstration in refrigerators. And the 4th pilot is related with washing machine door seals. Right now, we are in our first year of the project. We just finished our first year because the project started in May 2022. The Primus project has a duration of 3 years with a budget of almost 7 million euros, being a research innovation action with TRLs of from 3 to 6. We have 10 partners with 2 associated entities in 6 countries, as you can see in the map over here. Then, to be a little bit to talk about the objective of Primus, we will increase the sustainable use of production of quality, safe, and circular plastic recyclates in added value products. So we will create quality and safe recyclates. We will support the use of recycled plastics as safe raw material. We will demonstrate the application of those recyclates in 4 demo cases in automotive and home appliance. And we will support the recyclates market with debromination pretreatments and analytics. So if you want to know a little bit more of the project, then follow us, because we're still in month 13 and we have 2 years to go. You can join our stakeholders group. You can find in our webpage the industry or citizens stakeholder group. And that's it for my part. Then we will move forward to the second part of the agenda, the legacy flame retardants in recycled plastics. So for this part, we'll have Lane Tag and Tom Carries presenting this part. And I would like to introduce Lane and Tom. Lane works as a sustainability director at ICL. He holds various degrees in chemical engineering process and construction engineering, and a postgraduate qualification in polymer technology. He started his career in 1968 at Dow Chemical and moved in 1993 to ICL IP Europe as process project engineering for flame retardants. He is a member of the SWIG and OEWG within the Basel Convention since 2012, and since 2015 is a co-founder of PS Loop. He co-started in 2016 the cooperative polyestyrene loop for the demo plant and leading as managing director till 2021. Thank you, Lane, for being here. And for Tom, he participates in Primus project as well as creative projects and works at Coolrec as manager business development. He holds a master in mechanical engineering and started working at Coolrec in 2011 as technical project manager and later a project manager. Since 2020, he is responsible for business development, which encompasses R&D and regulatory matters. Since 2012, he is member of Senelec. Since 2019, as chairman of the We Label Advisory Committee. And since 2021, he is on the board of ERA and Plastic Recycling Europe. Thank you, Lane, and thank you, Tom. Please, you can start presenting. Well, before Tom, sorry, I will tell a little bit of the agenda of this presentation. Tom will present the legacy flame retardants in recycled plastic, And later on, Lane will present the historical use of flame retardants in legacy substances, the current situation and new trends, the challenges and opportunities associated with the legacy flame retardants, and then some conclusions. So, Tom, thank you for being here. If you can take the control of the presentation.
Yes, thank you, Carolina. Good morning, everybody. If we look at recycled plastics in electronics and flame retardants in electronics, we can see here per treatment category what the different polymers are that you can find in them, what their composition is, and where brominated flame retardants are relevant in those streams. And as you can see, where they are really relevant is in screens and monitors, both the old CRT tubes, the glass tubes for the older people among us, and in the flat panel displays that we all know today. And you also find them very much relevant in all kinds of small equipment and IT equipment. I do need to say that not all of these flame retardants, of course, are regulated, but these are today where we find those flame retardants. If we then look at the whole WEEE plastics mass flow, as you can see on the left, we have the mass flow of WEEE plastics. If you look at all the WEEE generated, you see that roughly half of that WEEE is collected in Europe in the known collection systems via municipal sites, via retail. And from those plastics in that WEEE, roughly half is recycled. So from the total mass of WEEE plastic waste arising, roughly 22% is actually being recycled today. The rest ends up in incineration and landfill, partly because some polymers are not recyclable, partly because some polymers cannot be recycled because they contain regulated substances, but also partly because some people just don't collect their waste properly or separate their waste properly, and the WEEE ends up in the wrong channels. And what is even more concerning is that still a big part of all the WEEE that is generated, and thus the plastics that are arising from that WEEE, either end up in what we call complementary treatment. That means treatment that is not in line or may not be in line with existing legislation, and a big part is still undocumented. So that means we do not know where it ends up. If we then go to the right, we see that same mass flow, but then focusing only on the brominated flame retardants in those plastics. And as you can see again from the part that is collected properly via the known channels and treated properly in line with legislation, where you see 22% of the plastics are actually being recycled, the actual bromine that ends up in this recycled plastics is less than 1% of this total mass flow. So in fact, you see that where we are having brominated flame retardants that might end up in improper treatment, or that might end up in landfill, in the environment, or wherever it should not be, then it is not going from the properly collected streams, but then we really should look in the WEEE that has not been properly sorted and collected. That is where in the protection of the environment and protection of the health and safety of the European citizens, where we can still make a big difference. And then we go to the history of flame retardants. Lane, please.
Thanks, Tom. So I also would like to thank Primus and Creator that was able to give a short presentation about the legacy flame retardants, and I continue more or less where Tom has ended. Just a short introduction about ICLIP. We are one of the largest flame retardant producers in the world, And beside the legacy flame retardants from the last 40, 50 years, we have a continuous flow of new flame retardants as well, brominated ones as well, also other flame retardants. And what we see is that through the years in the E&E, that we are using different flame retardants. But as you can see here, ICL is not only delivering the flame retardants for the E&E, but also in other applications like building and construction, the insulation foams, where about more than 90% is halogenated flame retardant. Also for textiles, also more than 90% is halogenated ones. It is an E&E, mainly the focus on ABS and HIPs, where we are also using halogenated flame retardants. Here you see the overview of the variety of flame retardants, and all of them are used in E&E. But also, for example, in wire and cable, aluminum trihydrate and magnesium hydroxide, and there you have concentrations up to 60%. If you are looking for the recycling of electronic waste and the FR fractions, then we see here that you have a complete pile where you have, for example, the brominated flame retardants around the ABS and the HIPs, but also you can find the brominated flame retardants in polypropylene and PCABS and ABS. The PC and PCABS is the phosphor flame retardant. But if you are looking to the total volumes and the total overview, then only a certain fraction ends up via density separation in the same basket. So it is dictated by the sorting technology, which starts with a density separation. That is what the Colrec is doing. Then you have a pile of the heavy fraction, and that is the fraction where we have to work with. If you are looking for the different categories that we do have in Europe, then we are talking about temperature exchange equipment, the large equipment. We call it the white good, like refrigerators and washing machines. And then you have the screen and monitors. Then you have small equipment and IT and communication equipment. But for example, you also have the professional equipment, like professional copiers, the rank Xerox. They are also using ABS and PCABS with flame retardants. So although we are always looking about the wee plastics from consumers, we also have, of course, professional use, which is ending up sometimes in the same flow. If you are talking about the flame retardants and what type of flame retardants we do find, Tom already said something about it, but you see the different fractions and you see that ABS and HIPs always is halogenated. And the main reason is because to achieve a V0, you need to have a minimum flame retardancy, and that is something you cannot achieve in ABS and HIPs with other flame retardants if you would like to have a certain concentration of the physical properties left. If you are looking for the persistent organic pollutants from the past, we know that we find them in the CRTs and the LCDs, the TV screens. It is minor because most of them were produced after 2000, the year 2000. So we did in a study 700 TVs, and we hardly found at that time any legacy flame retardants. If you are looking for the technical flame retardants, then finally the question is, why are these used? They are often used of the requirement of fire safety standards. So it's not that they just like it, but it's just to save lives. Most of the time it is because the electrical and electronic equipment contains a heating element, because of the chance of electrical shortcut close to plastics. So like in a TV, the distance between 220 volt and the plastics is sometimes only 3 millimeters. Styrenics are the main polymers where the brominated flame retardants are used, and typically it is used with antimony trioxide as a synergist. And if you're talking about the PCABS and HIPS PPO, there we are using the phosphor flame retardants. And I will come later to the different types, but they are also using PTFE as an anti-dripping agent between 0.2 0.4%. So what type of flame retardants are used and were used? The main historical flame retardant were the polybrominated diphenyl ethers, where DECA was the working horse for many, many years. And DECA itself was not seen as toxic, but the breaking down products into octa and penta were the main concern. TBBA and the derivatives. So TBBA is used a lot in ABS. 8-BCD was a minor use. And then you also have the brominated polystyrene phenols and the phthalic anhydrides. About the phosphor flame retardants used in HIPS PPO plus PCABS, that's mainly the resorcinol diphenyl phosphate or the bisphenol A diphenyl phosphate. And that are more or less the only two that are used today in these engineering plastics. During sorting, all these flame retardants are all ending up in the heavy fraction. If you are looking for the brominated flame retardant, what is the trend in the future? You see more and more going into reactive use, that you have cross-linking, but you also see the trend in polymeric flame retardants. It is important to understand all the different types of flame retardant used, and the main reason for that is if you have all the processes that we are trying to develop, the solvent-based purification processes. I'm involved with that since 2003. And what we see is that the solubility of the different flame retardants are also crucial how to separate them. If you are looking the presence of brominated flame retardant in V plastics, then especially in the CRT monitors, historical use was octa-BDE. And octa-BDE was used because it is melt blendable and it was very easy to handle. When octa-BDE was restricted, the main alternative was TBBPA. And after that, we moved into much more newer flame retardants, like which are recently developed, like the tretrimophenyltriazine, the FR245 from ICL, but also you have from the other brominated flame retardant producers, several types which are used in ABS today, always combined with antimony trioxide as a synergist. If you're talking about HIPS plastics, that one of the major applications was TV back panels. There for a very long time, DECA BDE is now part of the POP PDs, were used for a very long time because it contained the highest bromine concentration of 83%. It is replaced by decabromidiphenyl 810, and that is at the moment in use as the alternative working horse. There was a very minor use of 8-BCD, which today is a POP. The main use of 8-BCD is in insulation material. And that's the reason why you hardly find any 8-BCD in HIPS. So far, we didn't find any, actually. The BFRs are also in HIPS always combined with antimony trioxide. TBBA is also the basis of reactive BFRs, like used in printed circuit boards, and to produce brominated epoxies and other BFRs derivatives. To summarize, if you're talking about legacy substances, you also would like to know how finally you would like to remove these. And what we know is that it's a big challenge. As I said, we are already working on dissolution purification processes since 2000, and I was involved since 2003. And I had the pleasure around 2015 with EPS as an example, with only one plastic polymer type, with only one brominated flame retardant, to work together with Fraunhofer IVV and the whole EPS value chain. to produce finally a process or to establish a process where we were able to separate the brominated flame retardant from the polystyrene. And for pop containing waste, it is crucial to understand it is not about recycling. It is about the main job is to destruct the persistent organic pollutant. And today, what is only allowed is thermal processes. That means you need to have a temperature above 850 degrees with a residence time longer than 2 seconds. And we were able in the past to start up this process. Because of the energy prices, we had to stop the process, and it was reopened, and it's now successful running and able to achieve an HBCD below 100 ppms. It is still a challenge to see if this continuous process also can become economical and to be able to scale up. The HBCD sludge is separated via the process, the Creosols process, and is moving to ICL. We are the neighbor directly next to it, and we have a bromine recovery unit running as a hazardous waste incinerator at 1100 degrees, where the HBCD is converted into bromine, and the bromine is reused to produce a polymeric brominated flame retardant. So summarizing, the challenges for mechanical recycling due to scale of economy, sorting and quality is at the moment, it's nearly impossible to recycle these pop containing waste. Flame retardant plastic mostly ends up during sorting in the heavy fraction. And today, incineration or high temperature co-combustion is the only solution. Solvent-based purification processes are key to handle pop plastics. Within the Basel Convention, we were lucky after 4 or 5 years and support of the Dutch authorities and the European Commission to be able to get the solvent-based process as a pre-treatment step to be able to separate these pops. The available processes today are like the Creosols process, plastic to be cleaned, and other solvent-based purification processes which are under developing. But be aware, all those processes are at the moment at the level of pilot plants. What's also relevant is not all new recycled technologies are approved by the Basel Convention. So if we have new recycled technologies, especially in the area of chemical recycling, we have to apply studies with the destruction efficiency for the POPs, and that takes quite some time. Scaling up, timing and technical readiness are crucial, as it takes at least 5 to 7 years for scaling up from a pilot plant to a demo plant. And then a full-scale plant, you need to have investors, and all these steps are quite challenging, especially with the uncertainty about the UTCs and about availability of waste, and also if your process is accepted. So my role as ICL is to support and follow the flame retardant and recycle project, plus the interest of the pop destruction with bromine recovery at ICL Terneuzen.
Thank you, Lane, for your presentation and all the details and conclusions. Thank you for sharing the different techniques that are applicable for flame retardants. And we will continue for the second part, the third part, I'm sorry, of the agenda. Right now is the regulations and standards related with flame retardants. So for this part, we welcome Mathilde Tabot. Mathilde, thank you for being here. Mathilde is part of the Primus project, and she is the Primus regulatory work package leader. She holds a master in chemical engineering, specialized in materials and processes. Her graduation research was on the development of PP recyclates from old household appliances, led her to the plastic recycling world. So after working as a plastic engineer at a WE recycling facility, she is now focused on the chemicals legislation as well as on R&D projects at Plastic Recycled Europe. So welcome, Mathilde. Thank you for being here. Please take the control of the presentation, and we will start. Well, just to give some approaches of the agenda, she will talk about the current regulations and standards for legacy flame retardants, the changes in regulations and standards in recent years, and challenges and opportunities. So thank you.
Thank you very much, Carolina. So when we talk about regulation, and especially in relation with the flame retardants, first we have to place ourselves in the right type of legislation. So what you have to know first is that when we talk about recycling process, we are really at the interface between two types of legislation. We have first the waste legislation, because what is arriving at a recycling facility is a waste. And then we have a recycling process. During this recycling process, at some point, we reach what we call the end of waste status. It means that we fit some end of waste criteria in order to go out of the waste status and become a product. And therefore, on the second part, we have to comply with the product legislation. So the recycled plastic that is placed on the market has to comply with different product legislation. Here I listed a few. The one that we will talk about today mainly is the POP regulation, because we are talking about the flame retardant, and especially here the brominated flame retardants such as the PBDs, and therefore we will talk about the POP regulation. When we move on, a little bit too fast. And we look at the key problem that we may face in the stream of WEEE plastic is the fact that the product lifetime is quite long. So this is what you can see on the graph here. When we look at electrical and electronic equipment, it's kind of the same for building and construction, but it can go until like 10 years of lifetime. It means that when a product was placed on market 10 years before, it can be that in the meantime, the substance has been regulated. So therefore, 10 years later, when it's entering the recycling facility, this substance is regulated, and then it's up to the recycler to find a solution in order to sort those plastic and to make sure that the plastic they place on the market are compliant with the product legislation. And this is quite a challenge, because in the meantime, during those 10 years, quite a few substances can be actually regulated. And this is one of the specificity of this waste stream. So here, our job is really to find the best environmentally sound management of this plastic waste that is entering, and then to make sure that the output fraction then will comply with the product legislation. So that being in mind, then we will look at the different, let's say, regulatory process of one substance. And here we will talk about the brominated flame retardants and how they are listed and entering into the legislation. So the first step is regarding the Stockholm Convention. So what is the Stockholm Convention? It has been established for the persistent organic pollutants. So this is the acronym of the POP, in order to protect the human health and the environment on specific chemicals that have the listed properties here. So either they remain intact in the environment for very long periods. They can be like widely distributed. It means that they can also travel long distances. They can accumulate in and wildlife, and then they can have impact on the human health and on the environment. This is why mainly those substances are listed from the very beginning. And based on this, the Stockholm Convention was created, also because since those substances can actually travel, it's not up to one member state really to do the job, but rather an overall solution, because the substance does not stay in one member state, and therefore it's relevant here to build the Stockholm Convention in order to eliminate the POPs from the environment. How is it working? So first, those substances are listed in the Stockholm Convention. There is different annexes. One annex that is called elimination, and then currently there is roughly 30 POP substances that are listed across the different annexes. And once this has been listed in the Stockholm Convention, then this is where we move on at European level, and then we enter what we call the POPs regulation, which is a regulation at European level. And that's what we will see in the second step, where we have the implementation of specific rules and regulation for those POP substances that have been listed in the Stockholm Convention. So once it has been listed, it is written that it must be eliminated. How to do so? The POPs regulation is there for this purpose. There is a threshold very often that is placed on this substance, and this threshold is related to the product legislation. And then you have a second threshold that is on the waste legislation, because the POPs regulation is acting on both fraction, both on the waste and on the product fraction. And that's what we are going to see just afterwards. So the one called Annex 4 is the annex that is related to the waste fraction. So here we define a specific threshold that is applicable for the waste fraction. It means that if a waste is exhibiting a concentration that is above a threshold for a particular substance, then this fraction will be considered a POP waste. The fate of a POP waste is that it needs to be destroyed unless you can prove further that you can actually separate it and cluster more the POP in one fraction that will be destroyed, provided that the second fraction will be compliant with the POPs regulation Annex 1, so on the product. We call them two different limits. So the one on the waste is called the low POP content limit. And the second one that we see afterwards on the Annex 1, so on the product legislation, this one is called the unintentional trace contaminant limit. And then for this fraction, when you have a certain substance and you would be above, it means that you cannot place this product on the market because you would not comply with the product legislation. And this is what is here. You also have to know that at the moment, those limits are different in Annex 1 and in Annex 4 because those two different annexes can have different threshold and different limits. So this is this. Then when we look at the recycling process and how it works based on the limits that we have discussed just before. So here it's a theoretical example, so do not mind the concentration that are there. They're just there for the purpose to explain the recycling process. What is entering very often the recycling facility is already a POP waste, and it's meant to be treated and separated. In order to have one fraction that is compliant with the product legislation. That's the one you see in green that needs to be below 500 ppm for the sum of the PBDs. So that's the substance that is mentioned here. It's a flame retardant, as Line explained before. And then we have a rest fraction. This fraction concentrates the POP substances, and this fraction is to be destroyed. It's a waste fraction. It's a POP waste that can no longer be separated because at the moment there is no technology to do so. And therefore, it is currently destroyed. Of course, there is innovation in the future, like Line has presented. So maybe like dissolution processes will be able to treat this fraction in the future, but at the moment it's being destroyed and therefore it's going to incineration. So there we really have two fractions, one fraction product compliant with the product legislation and one fraction waste that needs to be destroyed in order to be compliant with the Annex 4 on the waste. So it's quite a complex legislation really at the interface between, let's say, input and output of the recycling process, but quite relevant to understand when we have a look at this legislation. And then on the last step, it's really to understand that these limits are reviewed quite frequently. And the idea is how to find the best compromise in order, of course, let's say fit the main objective of the Stockholm Convention and the POPs regulation is to eliminate those substances. It's very important. It's a key factor. And on the other way, it's also understanding that the recycling process has a lot of benefits, and of course are able to separate those two fractions and treat accordingly the POP waste by sending it to incineration and clustering the POPs in one fraction. And is also bringing a lot of environmental benefit, of course, by recycling the plastic. So it's how to find the best compromise when we review those limits. So at present, the limit in the product fraction is set at 500 ppm. It's meant to be reviewed because also something to understand is that there is the obligation to review the thresholds that are listed in the POPs regulation. Therefore, it's important to review them regularly. And there is the process in the EU legislation to do so. And then on the second annex on the waste, there has been a review that is going through a different legislative process. And this is the limit that you can see now. What has been implemented is a kind of timeline with threshold that would gradually reduce through time. And this is what you can see here. So at the moment, we have also a limit on 500 ppm. And this is quite the point that we would like to bring also afterwards. The relevance on finding the right balance. The industry do believe that having an alignment between both the waste annex and the product annex would be quite relevant to have a gradual reduction of this threshold, but still some clarity on the limit values, and also having still a little bit more time with a threshold at 500 ppm in order to develop the processes, but also taking into consideration the accuracy and representativeness of the analytical method that is currently available. And therefore link, of course, to the enforcement of these limits, by still bearing in mind that there is an obligation to review those limits, of course, and that we also have to consider the technology that is currently available in most of the member states, being today mechanical recycling processes, even though there is a lot of innovation going further and forward, which is a very good thing, but still considering those limits and the treatment that is applicable today, this is a kind of recommendation. And then we have the very important point of the analytical methods, and then it will be the part that will be discussed by Tom afterwards, but it's also a very important point because in order to comply, we need to have a tool that can prove that we comply to those limits, and this is the big point, let's say, that Tom will talk about afterwards. So with this slide, I would like to thank you very much for your attention. And of course, if you have some question, you can write them in the chat. And then I will let the word to my colleagues. Thank you very much.
Thank you, Mathilde, and thank you for sticking to the time in the agenda. And I really liked your presentations because you are so clear. Thank you for explaining us the different steps of the standards and the process. So we will move forward to the next part of the agenda. Tom Carries will explain the testing, analysis, and best practices of. Can you move forward then, Tom?
Yep, sorry.
Thank you. No worries. I already explained Tom's career, but as a kind reminder, well, he works in Coolrec and he is part of the Creator and Primus project, and he will talk about the techniques of testing and analyzing legacy frame retardants in recycled plastic. He will present different use cases or example of testing and analysis and some best practices for manufacturers and recyclers. So the floor is yours, Tom, and thank you for being here.
Yep, thank you, Carolina, and thank you, Mathilde, for that great introduction to what I want to tell and what I want to talk about. Because it is indeed, as Mathilde says, this as a recycler, we are a recycler of WEEE, and we are a recycler of WEEE plastics. The key is that we have to prove that we are compliant to existing legislation. And if you look at current legislation in Europe, if you count up REACH, if you count up POP substances, if you count up the substances of very high concern, you will see that 600 to 700 different substances are being regulated. And of course, you can imagine that if you were asked to ask me as a recycler, can you analyze each and every fraction on all these substances, then I would have to say, no, it is way too expensive and I will never be able to compete with virgin material if I have to do that. So what is then recyclers? What are recyclers doing actually in reality? That is the big question, and it is something that we saw within Plastics Recyclers Europe as one of the key things we needed to work on. So with Plastics Recyclers Europe, in the past couple of years, we have developed a screening and analysis methodology. It's a standard. At the moment, still an industry standard. It is not yet ready as a European harmonized standard, but we are still working on it. And in this standard, we are actually looking at where is the waste coming from, what kind of substances are we expecting in there, and how can we screen those substances to be able to prove as a recycler that you are actually compliant with all existing chemical legislation. So this whole standard encompasses a part literature study, a part sampling, a part analysis, and a part screening. For instance, if what we can use in the screening is a simple X-ray fluorescence analysis. That is a quite cheap analysis that most recyclers also have in-house. To go back to the example of the brominated flame retardants, for instance, if you would take HBCD as a flame retardant, take a regulatory limit of 100 ppm, you know the chemical composition or the chemical formula of HBCD, then you know that 74.7% of that mass of the HBCD molecule is bromine. So if with your XRF analyzer you can measure that the total bromine content is below 74 ppm, you can guarantee that if that bromine, all that bromine would be coming from HBCD, you would still not be over the regulatory limit. So with the simple XRF analysis, you can already eliminate a lot of substances of concern that might be in the waste or in the product that you're dealing with. Other factors that we are looking at are, for instance, physical chemical properties. Product with a boiling point of 50 degrees will no longer be there if you treat a plastic, if you injection mold a plastic at 200 degrees. You look at historic use. For instance, a pesticide in agriculture, you will not find it in plastics, and so on and so on. Or a plasticizer that has been designed for PVC, you will not find it in ABS. So, and by this way, we can screen a lot of substances. This whole method is, like I said, we developed it, and at Coolrec we were one of the first to start using it. And by using it, you improve it and you build up knowledge about the method, and you quite quickly see some problems that you need to work on. And we decided to continue this work and to improve the standard further in the Primus project, which is running still today. Mathilde already explained to you that in her last slide, this accuracy of analysis is, or the accuracy of being able to prove a certain value is key. And if you would look at the whole chain of how is the sample produced, how is it analyzed, and so on, you see that it is a sum of different inaccuracies. And it already starts at the sampling. As we explained in the beginning, we plastics are a very heterogeneous stream. So you have all kinds of polymers in there. You have polymers with flame retardants, you have polymers with no flame retardants. And if you see from the presentation that Lane gave, you saw that You have a lot of plastics without flame retardant, and then you have some plastics which contain flame retardant. But when they contain a flame retardant, they contain them in a very high quantity. And this was actually studied in a study performed by INERIS, by Mr. Pierre Hennebert, a few years ago, where he looked at sampling from a statistical point of view. And that's actually quite interesting. What you see here on top is a histogram where you put all the particles of plastics with their bromine content. And as you can see, on the left a huge peak of plastics with 0 bromine, and then you see a very long tail of small amounts of plastics with very high bromine contents. If you put them on a cumulative histogram, what you see on the right, you will see that in hundreds of particles that you are sampling, that one last particle, that one single particle that you add can give a very big difference in the actual bromine content in your sample. So one extra particle can make the difference, or two different extra particles can make the difference between a bromine content of 86 ppm or a bromine content of 2,000 to 3,000 ppm. So as you see, this representativeness of a sample is very important. What you see here, these two histograms, is on the wee plastic, so that is the raw input of mixed polymers with different flame retardants and so on. If you would apply that same methodology on the output, so a pure polystyrene, for instance, after sorting, where of course you sort out all the particles with the bromine content, and like sorting is never 100%, so there is always 1 or 2 particles that you miss. Then again, here you see that one single particle extra can be the difference between a 30 ppm content or a 240 ppm content. So as you see, sampling is extremely important, and the representativeness of the sample is extremely important to be able to give a guarantee on certain contents of substances of concern. Now, this is, like I said, this is an explanation or a study that was done on brominated flame retardants, but actually this logic, this methodology, you can apply it to any kind of regulated substance. So what does it mean? And that's also in the same study, Mr. Hennebert actually defined, just using basic statistics, how big the sample must be to be representative. And if you look at a basic statistical rule, if you want to have a variability or an accuracy of 10%, then in your total sample, you need 100 particles of interest. If you would calculate that back to the raw plastic mix, where the POP Annex 4 is counting, as Matilda explained, that would lead to a sample that would be at least 1 ton, 1,000 kilogram. If you would look at our output from plastics recycling, then it would be a 100 kilogram sample. So that is where the Annex 1 of the POP regulation is counting. And of course, it's obvious there is no laboratory in the world that can handle this amount of sample. So something theoretically would be needed. If you would have to reduce that to a laboratory sample, which is maybe 1 kilogram or 10 kilogram maximum, then you would have to do a size reduction on the sample. Because also in that sample that goes to the laboratory, you want 100 particles of interest. So this size reduction, it would mean in theory that we would need installations at every recycler to do size reduction and subsampling to be able to send to a laboratory. And then at the laboratory, again, you need to do size reduction and subsampling, because the sample that is analyzed in the laboratory is only 1 gram or less than 1 gram. So as you can see, for very low limit values in the POP regulation, you need big investments in sampling, big investments that today nobody has done. Of course, we realized this, and within the method that we have developed for screening and analysis at Plastics Recyclers Europe, we decided to look for alternatives. And those alternatives we are investigating in the Primus project. So how can we homogenize this very heterogeneous material in order to come to a sample size that is that a laboratory can handle? It is a study that we are still performing, that is still ongoing. We have defined different sampling strategies, and we are testing them and assessing the different scenarios that are possible within those strategies to compare them, and in the end define the most accurate sampling methodology that we can follow. And one example of one of our failures, I have to say, that we already found, we believed originally that if we would injection mold the material, that we could homogenize the material. And what we found out, you see here on this photo, we just took white material and introduced a few black particles, injection molded them, and we checked, is it homogeneous? And as you can see from the photo, it is not homogeneous. So this is not a good methodology. We need more, we need better than this. And like I said, this is something that is ongoing, and we hope by the end of the, or we aim by the end of the Primus project to be able to present a much better and a much more accurate homogenization and sampling methodology. The next step, once you have a sample, is you need to go to a laboratory. And it starts with selecting a laboratory. Because already the selection of the laboratory is important. There are standards available for certain analysis. And if you would ask two chemists to perform the same analysis, they always will come with different results. That's basic rule. That is how it works. What is important is that you have a variability intra-laboratory. So if the same laboratory, two different chemists within the same laboratory are performing an analysis, then they find a difference, but they are using mostly the same methodology. So the difference is within the person and not so much the methodology. But you can have also a difference inter-laboratory, saying between different laboratories, they are maybe using slightly different methodologies, so also leading to different results. So those deviations may be important and need to be taken into account. If you look, for instance, at the analysis standard, that's a European standard that is used for brominated flame retardants, then here you can see a study that was performed by Arthur Haarman, where he checked the inter-laboratory variability on this analysis. So he found a standard deviation of 0.2, which is in fact acceptable, with a maximum of 0.36, which is already on the limit, but the 0.2 is actually acceptable. This looks good, but you have to see that this study was performed with reference material, meaning a known virgin polymer with one known brominated flame retardant. If you go to waste, you introduce different kinds of polymers from different suppliers, slightly different composition. For instance, we always talk about the pure ABS in recycling, but in fact, it's never 100% pure. It is always a mix of ABS with SAN and ASA. There is emulsion polymerized, emulsion-based ABS. There is mass polymerized ABS in there, so slightly different chemical structure. But there is also impurities from polystyrene, small impurities of polypropylene, and so on in there. And the same goes for the flame retardants. There are different kinds of flame retardants. Every possible brominated flame retardants that has been used in these polymers may be present there, as well as other additives, as pigments, as any kind of lubricants, you name it, it might all be in there. And that all has an effect. So there, Mr. Hennebert performed a study again to compare laboratory results for that same standard on brominated flame retardant, and he found a intra-laboratory variability, which was 0.16, again, which is acceptable, but already with peaks up to 0.64, which is too much. But that is intra-laboratory. So what would that mean for inter-laboratory variability with real plastic waste? And that study has never been performed. But we can compare with other substances, with other standards, where both the intra and interlaboratory variability have been checked. And as you can see from the table below, there usually is the interlaboratory variability usually is quite a bit bigger than the intralaboratory variability. So if you would extrapolate this to this EN standard for analyzing brominated flame retardants, you could expect that the inter-laboratory variability will probably be in the range of 0.3, 0.4, which is unacceptable, which is too high. And that is important to know. And that is something that we encountered within the Creator project. While developing analysis methodologies or comparing analysis methodology was not really the aim of the Creator project, we noticed that in comparing the analysis results from the different partners, developing partners in the Creator project, we noticed that the results varied hugely. At a certain point, this difference was so big that we decided to do a sort of ring test using different standards and using reference material again. And what we found out that it is in fact the standard itself, the EN standard itself, which leaves too much liberty to the laboratory in selecting the solvent, in selecting the parameters for the equipment and so on, that led to big variability in the results. Within Creator, and I say we, but it's actually a team of different partners led by Kevin, developed a new protocol for analyzing the HBCD content in these waste plastics. And that was one that gave an extremely good accuracy. So a detection accuracy of plus minus 0.05 weight percent. That's really fantastic. I have to say, however, that we found out that although this methodology works very well for HBCD, it did not give the same accuracy for the PBDEs. And there, of course, we will need to develop a new standard also, because also in the PBDEs, we noticed that there was big variability of the results. So we really need the development of a new standard also for that analysis. And for that, as Kevin said, the Creator project ended yesterday. This development was not foreseen, not in the Creator project, not in the Primus project. So we are at this moment actually looking for funding to develop this standard further. So all this looks a bit a sad story. Telling you what can't be done, but actually a lot can be done. If we look at Coolrec ourselves, like I said, we have been using this PRE method, and we have been trying to further improve these methodologies. And if you apply all this, at Coolrec, we managed to be one of the first recyclers in the Netherlands to receive an official end-of-waste status by the local authorities for our recycled plastics, just by using this methodology and by developing this also further. And if you look what this success leads to, it is actually by major brands in Europe introducing our recycled plastics in their products, and not just small brands, but premium brands like Playmobil, like Electrolux, where we have our recycled material in the inner liner of a refrigerator, and Legrand using our material in electrical cabinets. And what makes us successful then? And that is really in working together with the customer, understanding what is possible with recycling and understanding what is not possible. But also for the recycler to understand what the customer needs. And please be aware that there is a difference between what the customer is expecting and what the customer really needs. And in the end, it's from both sides, both from the recycler and from the producer, adapting the expectations, not really lowering, but adapting, so to make the impossible possible. So it's really this joint journey which makes it all possible. Thank you very much. And now I am really looking forward to the questions.
Thank you, Tom. This is quite interesting, and thank you for explaining the best practices and the failures, because that is important as well. Just to tell what had been done and what we can't work at this time. So I will take the control of the presentation, and we will move forward to the next part. This is the roundtable. So we will be asking our presenters two main questions. First one for Lane and Tom. Well, after your presentations, we're looking ahead, and there are actual substances being banned in the coming years. So what are the consequences of that?
Yes, thank you, Carolina. Maybe I can start. There are two sides to that. The one side to what are the consequences. I think the main consequence depends on what Matilda already said, is what is the level of the limit value that will be selected in regulation, and are we as an industry able to prove that compliance to that limit value? I think that is the first point that I would like to make. And as we explained for the past hour, that is something that we are really working on to be able to prove that. Another consequence is, or another potential consequence, is something that we have to be really careful of. It is something that in our industry we started calling regrettable substitution. What we have found out looking back into the past is that very often the substitute of a substance that has been banned gets under investigation and is potential substance for a future ban. So we always have to be aware that the substitutes that we introduce today for the substances that are banned today, that if they get banned in the future, that we will still be able to sort them out. And one of the evolutions that is really of concern to me is the flame retardants that are being developed today. One of the things that Lane already explained in his presentation is that in our industry we are working on solvent-based recovery, where you can remove the flame retardant from the polymer. But if you would go to polymeric flame retardants, of course, you will not be able to remove them by solvent-based recovery anymore. So we have to be conscious about that. If with what we develop, that we are not blocking the developments of the future. The second thing is the non-halogenated flame retardants, and that's concerning me more. I think one of the main advantages of brominated flame retardants, and many people might not like me saying this, is that they are easy to separate. They have a higher density, so we can simply sort them by density sorting. And at the same time, bromine is a heavy element, so you can see them with X-ray technology. So there are two technologies today at industrial scale which we can use to separate them. Today we see a move from the brominated flame retardants towards the non-halogenated flame retardants. And very often there what we see is that they don't change the density, or not so much, and that they are not containing heavy elements that are detectable with X-ray technology. So today we do not have sorting technology available at industrial scale, and not even under development at a pilot scale, to sort out plastics containing these flame retardants. So I'm really calling on the producing industry to start thinking about how can we mark these materials so that we always will have a solution to sort them out. That can be either by just adding something that changes the density, but that can also be by adding a kind of marker that is visible by sensor technologies.
Maybe I also can give 2 points. First of all, it all depends if the future restricted substances are ending up in the heavy fraction or in the light fraction. If it's in the heavy fraction, then they could be treated similar like all the other flame retardant and other heavy additives. But if it ends up, for example, in polyolefins, like maybe in the future titanium oxide, then it will be much more problematic for Colrec. The second remark is about if you are sorting your ABS with polymeric flame retardants and they are going into a dissolution purification process, then the polymeric brominated flame retardant are passing the process, and as it is not a restricted substance, it can be reused and it can be recycled by adding an additional amount of brominated flame retardant, and by that you have the same quality and final virgin similar quality that can be reused.
Thank you, Tom and Lane. I think that one of the remarks that Tom said and pointed out to the industry is the importance of creating a better sorting technology that the audience and can relate, and that it's quite important for the future, near future. Maybe we can move forward to the second question of the roundtable, and this is more related to the presentation of Matilde. It is expected to have forthcoming updates in regulations and standards affecting the flame retardant substitutes.
Yeah. So on this, indeed, there is some ongoing work in order to work on regulation or restriction that are targeting a family of substances, let's say. So, for example, there is a family of substance, for example, the brominated flame retardants, and then within this family, then can be some prioritization of the substances in order to restrict them. But that's important also to have a view of the substances as a family, because as Tom said, we can have some regrettable substitution, especially when developing new material. The second point that is relevant to think about here is also we talk a lot about design for recycling based on the product, but there is also design for recycling for the material. A material is a polymer and an additive. It forms a plastic. It's also how we design this plastic so that afterwards it can, during its end of life, it can be recycled properly. And that's by taking into consideration all the different end-of-life processes that can exist, and also all the regulation that are applicable. And I think, therefore, like some collaboration between the industry is very relevant on this point, so that we ensure that we develop things that do not trouble us afterwards, like it is the case for some of the substances today, because, of course, the plastic recycler, they're not using those substances. The substances are ending up in the input waste. It's up to us then to sort them, but we did not add those substances in the very beginning. So it's important also for us to have a cleaner input waste in the future. This is also why those regulation and restriction are very important for the industry.
Thank you, Matilda. So I can highlight like 2 points in your answer. The first one, it's important to check the prioritization of the substances and the families as well, where the substances are. And the second one is the design for recycling for the materials, not just for the product, but also recycling for the materials and having secondary raw material as clean as we can for the sorting process. So thank you. I don't know if Lane, Tom, or Kevin wants to add something to the first or second question. Nope. Okay, so we will continue to the last part of the presentation. So this last part is the questions of the attendees. My colleague Etienne has been collecting all the questions in the chat, and if you can share the questions, please. Okay. Okay, so for the first presentation, Lane, you have 2 questions in slide number 19, that is titled "Recycling of Electronic Waste as Flame Retardant Fraction." They ask, is the average composition of the WE of plastic for recycling at a European view?
It's correct. It's the European view. Yeah.
Is a
I do not really have global overview so far. We do have information from the US.
Okay, but in the presentation we just saw the European view, because in the
Correct.
slide number 20 we were talking about the European, but in slide 19 it wasn't clear, so I guess the question was related with that. And the second question for you, Lane, is what are the potential consequences of EU PFAS ban?
At the moment, the link between PFAS and PTFE. PTFE is an anti-trapping agent that is used in PCABS and HIPS PPO. And at the moment, at least, that's the information from a study I heard from Fraunhofer, that there is no link or any contaminants from PTFE linked to PFAS. So that means for the moment, for our V plastics, we do not see a concern. Maybe Tom has other background, but at least PFAS as such is not directly used in V plastics.
Yeah, we are doing analysis, and maybe Mathilde can add, because she has more insight, and also what other recyclers have been analyzing. We do find some PFAS or potential PFAS, because it's still not clear which substances will be included in the ban exactly and which not, in WE plastic waste. But up to now, what we have found was low concentration. So at the moment, I'm not concerned.
But maybe to Mathilde, the low concentrations, if you see the low pop limit concentration for the PFAS presented at the Basel Convention, then it's going down, 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 and it could become a problem in the future.
Indeed, so the concentration that have been listed at the moment are very low. It can be considered as a trace, to be honest. Therefore, this is more the concerning thing, also because it has been used in processing aids, and therefore traces can be present. So this is something that is currently being investigated. And also because PFAS is a family of substances in which you have individual PFAS. They're not all identified. It means they have a fluorine, let's say, a bond, part of the chain. And because those have not been identified, it's very difficult to analyze a substance that is kind of an unknown in the molecule and, let's say, the design of the molecule. So this is more the challenges, also a part of analytics, of course. This is also another example that can be quite challenges to analyze.
Thank you, Tom, Lane, and Mathilde. I think that it is clear now. Maybe we can continue to the questions that approach and that popped in the roundtable. So the first one was after Tom's and Lane's answers of the first question. It says, is the polymeric flame retardants can be dealt via your solution process or not? Seems different views provided here.
No, it are not different views. It is the challenge that we will face in the future, as we also see with the PS loop, is that you need to have more analysis and more control during the process, where you normally screen with XRF on bromine. Now it's not only screening the bromine with XRF, but you also have to analyze. So it's a little bit more complicated to run the process and to check reach on your product. Maybe Tom has some additional info.
Yeah, there is that, and there is, of course, what is legislation doing? If we are moving towards a complete ban, of all brominated substance, like a family ban, as is now being proposed with PFAS, then you might get also a ban on polymeric flame retardants. And like I said, the dissolution process will not be able to remove them. So we really have to look carefully in how the regulation moves to avoid that we cancel actually years of development of new processes and millions that have been spent in developing these processes to resolve these issues.
Yeah, so far at least, polymeric flame retardant and reactive brominated flame retardant are not part of a proposed one.
Okay, thank you both. Then the second question is for you, Tom. How is collaboration with the plastic industry being managed? Because we hear Tom saying they're worried about new flame retardants being developed, clashing with what's technique being developed at Coolrec. Is collaboration between the different interest partners not an option? It is an option.
Well, I'd immediately like to ping pong this to Matilda, because that's where our federations come in, our associations come in. That's partly also their role. Maybe one point, it may not be a widely spread message yet that we gave here a few minutes ago, but that's mainly because it's a point that we only just recently put on the agenda. So we are going to start discussing this with different industry partners, but we only just start with it.
Yeah. I can add that, of course, we are collaborating throughout the whole plastic value chain and working together in order to find solutions. So yes, definitely, we are talking to one another.
Yeah, it is an option. Thank you both. And then another question is, how will the proposed PFAS restriction influence plastic recycling? I think you already explained this, Matilda, but I don't know if you want to add anything else. No, I think that it's answered. And the last one is the poly BFR remains as a non-restricted flame retardant, but the final recyclate must be upgraded with additional BFRs sorry, I can't read all of this, V0 fire safe plastics.
It was the answer on the first question. It are not all questions. Also in the chat you see answers.
Oh, true. Yes, yeah, Lane. Thank you. You were answering it as well. Yes, the poly BFRs remain as a non-restricted flame retardant, but the final recyclate must be upgraded with additional BFRs. Okay. Yes, this was an answer. Yes, true. Thank you, all of you. Thank you for being here. I would like to share the last slide just for you to know. Wait a sec. Okay. Okay, so thank you all for being here. Thank you for participating in the second chapter of the Boston Plastic Recycling webinar series. And if you are willing to learn a little bit more, if you're interested on the creation and the content of these webinars, you can follow the Primus project and join us in our community. We have two communities, the stakeholder communities and the citizens one. So thank you all. Thank you, Tom, Kevin, Mathilde, and Lane for being part of this. You are the experts, and without your knowledge, we couldn't do this. So thank you. And thank you to all the attendees. We will be sharing the presentations and the video of the recording via email to all the registered people, and then we will be sharing as well the webinar in our webpage, our Primus webpage, our YouTube channel, and social media. So thank you all. Bye.